Hi, I'm Pete Gural. I'd like to describe an algorithm which works in the subspace domain called SLIDE to be applied to me. So what is a SLIDE algorithm? It is a subspace-based line detection that was published that looked at the analogy between the angle of estimation of lines in imagery to the angle of arrival estimation of planar electromagnetic waves impinging on a uniform line array. Basically, if you have a plane wave propagating from right to left, as it hits a series of sensors, there'll be a time delay between when each sensor would pick up the signal. It uses high-resolution angle of arrival techniques from the sensor array processing community, specifically the algorithm called SPRI. It takes advantage of the spatial coherence in the rows, or the adjacency of pixels along the line, to generate a signal subspace, and estimates multiple lines at various angles and offsets x naught. It'll work with both 2D binary images and grayscale images, and is designed around the fact that it's got low computational loading and storage requirements, which makes it ideal for the particular application I'm interested in. So, what's the motivation to try SLIDE? I've looked at a number of different algorithms over the last 2 decades, anywhere from doing very fast clustering with a multi-frame tracker, which is a current implementation of the Western Ontario, using pixel pair Huff transforms, using a beta-coded disk Huff transform, and it's going as far as using a matched filter, which is basically template matching a hypothesized motion to an actual streak over multiple frames. That is the one on the right there. Match filter is probably the most effective at getting the best measurement accuracy for leading pick point edges, but it's very, very, very slow. And so what we wanted was a very sensitive queuing detector at the front end to feed a match filter as a back-end post-detection process. SLIDE looks like it may fall between running a fast cluster approach versus a pixel pairing of transform. And so it had some attraction from a runtime perspective. So at the University of Western Ontario, I've been supporting their work on developing the EMCCD processing pipeline. What you see on the left is a detection application that I've built for them. It's referred to as DEDAP, and it involves a number of processing blocks here that all are very optimized in terms of runtime. But the bottom line is, if you look about 2/3 of the way down, there is a clustering detector and multi-frame tracker, which does the basic front-end detection, and that cues a matched filter for doing very fine track refinement and estimation of the leading edge pick points. There's a very extensive description of all of the processing steps involved here and the performance results. That's getting published. We just submitted this to the experimental astronomy. You can see the reference down at the bottom there. We should have the PDF actually by the time of this presentation. However, in order to determine whether or not we're working optimally, we decided to apply a pure brute force match filter to a data set from the EMCCD low light cameras. And we did see significant gains in detection if we would actually hypothesize all the possible motion templates for speeds and positions. However, to process 1 hour of data, it takes almost 3 weeks of runtime on a 64-node cluster. Nevertheless, you can see from the bar chart on the right that the detections out of DEDAP, which are in orange, get down to about 10 dB maximum likelihood estimate, whereas you go below that with the fully blown match filter implementation, get almost an extra magnitude out. Now, some of those lowest values are probably very difficult to try to find leading edge pick points on for a meteor track, but I would, and you see about a 3 times improvement in detecting meteors. Probably around a factor of 2 would be more realistic in terms of actually being able to measure the positions of each of the meteor tracks in each frame. So the first step in testing out the use of SLIDE as a front-end processor for meteor detection involved going through the algorithm and implementing the details. Now, I'm not going to go through all the expressions here. The bottom line is you need to form a covariance matrix from the imagery. And to do that, you basically just sum across columns, putting in a phase factor, which basically looks like a plane wave propagating across to a series of sensors on the left edge of your image. That creates a data matrix Z, which you then produce and compute an outer product, generate the covariance matrix, and do an eigen decomposition. The eigenvalues are basically broken up into the signal, into the noise components, and then you attempt to estimate the number of lines in the image by using one of many algorithms, but the one they recommend is the minimum description length algorithm. Has a complicated formula. That basically serves as the detector, and then you need to, once you have 0, 1, 2, 3 number of lines, you attempt to estimate the angles and the offsets using an algorithm called the spree, which basically just takes your signal subspace, does another type of eigen decomposition, and estimates the angle theta as well as the position offset x. All the details are in the 2 references that are listed on the bottom of the page. So, implemented this up in MATLAB and ran a test example using a simple line in a white Gaussian noise background. The line was at a position at an angle of 25 degrees. The eigen decomposition of the covariance matrix shows, is in the upper right plot there. It shows the signal clearly popped up above the noise eigenvalues, and the minimum description length algorithm worked very nicely. That circled blue dot in with the red circle is the number of lines that it estimated in the image, and it was 1, so that is correct. And when you actually went and calculate the angle, you get 25.069 degrees, which is very close to the actual input value that was known for the truth. So there are some issues associated with implementing the SLIDE algorithm. One of them is aliasing. You have to pick this mu naught, which is part of that phase factor that goes into the sum across the columns. And if you make it too large, you actually can end up with aliasing. So it's very often that they recommend you use a mu naught of 1, but that kind of limits you to have angles greater than 45, greater than or equal to 45 degrees. It's in the green image on the right there. However, if you have angles coming in more shallow, then you run into an aliasing problem. However, you can sort of do an image transpose or just sum down rows instead of across columns, and you can eliminate that the aliasing issue. However, if you do that, you have 2 potential solution sets. So you have to pick the largest eigenvalue to say which one is the more likely estimate for the meteor track. The other issue is we're doing a covariance estimate, and in the original paper, there was very limited sample support for generating that covariance estimate. However, there was a follow-on paper published about a year or 2 later that was able to increase the sample support by a factor of 4 to 5 times without destroying the actual signal subspace. And that was quite effective in producing better covariance estimates. So we tested this out on a simulation, which was based on the University of Western Ontario's low light EMCCD imagery set. So, but this is simulation based. It's pretty benign. It's just got white Gaussian noise in it. It does have stars. It has a Gaussian point spread function typical of the imagery that we were looking at. We simulated meteors with velocity from 1 to 35 pixels, motion of 1 to 35 pixels per frame. and a meteor duration that could last anywhere from 4 to up to 30 frames. And it had a variable SNR, and you could see what the SNR levels look like in terms of visualization of the meteor tracks there in the lower right. So, running the simulation, initially it looked like we had very good results. Doing a performance analysis on the ability for the algorithm to estimate the angle of arrival was extremely good, typically less than 1 degree error, but most of the time actually much less than that. It also, we found it wasn't terribly aliased unless we had meteors coming in at almost the horizontal direction. But again, you can mitigate that by just doing a transpose on the image and then processing it in the same way you had done before. However, when you started to take a look at the performance level in terms of signal to noise ratio and the length of the meteors, or the number of rows that are presented to the algorithm where the meteor is actually illuminated, you can see that those red crosses start to really run into a problem there with very, very short meteors where they don't actually span very many rows across the image. And you can see the blue dashed line is actually where our current existing DEDAP cluster detector operates. And so we were sitting way above that line. However, if you look at the plot on the right, it's a lot of the missed detections for short few number of rows has to do with the aliasing effect, basically at angles of plus or minus 90 degrees off the vertical. So we took a look at looking at results where we didn't have aliasing impacted. So we only looked at meteors that were simulated for angles of less than 45 degrees. But we're still having a problem there, even with the number of rows being, when they are fewer, it's basically missing very short and faint meteors, small SNR, small number of rows exposed to the image. However, we also took a look to see if the detection threshold that we're essentially using, which is the minimum description length threshold, was somehow eliminating some of our cases. And this turned out to be true. If we always forced the minimum description length to equal 1, then we actually started picking up more meteors at a lower SNR. However, it's still not reaching the performance of the current DEDAP cluster detector. What we believe is happening is the plane wave assumption is breaking down as meteors just don't span the entire focal plane. So, in conclusion, what we found is when a meteor does get detected with the SLIDE algorithm, you get really good angle estimation. And of course, that would help in terms of minimizing the number of match filter hypotheses you have to use to refine the position measurements of the track. However, the detection SNR performance was worse than the current existing codes that we have in place. It tends to miss a lot of short, faint meteors because the algorithm, although not described in the paper, does seem to require that a line span across the entire focal plane and not actually only span a subset of it. I tried various variations of the algorithm, looked at more deeper thresholds at the front end, actually processed only a small chip out of the image to try to avoid this issue of not spanning the focal plane, and try to detect shorter lines, and also looked at setting the MDL level to 1 signal at a time. All of these really did not get us down to the level of performance that we currently have with the DEDAP, and so unfortunately we would not be using this algorithm. Nevertheless, it was an interesting and fun exercise to have played with over the last year. All right, thank you.